start with just pull up some sketches that people submitted that I thought were interesting. There were a lot of very interesting ones, and if yours isn't up here, that doesn't mean it wasn't interesting. It just means I don't have time. So I'm going to start with just showing a few interesting sketches that were submitted Monday, and then I'm going to talk about a little detail that I kind of brushed over when we were using the array list on Monday. Some of you may have noticed it, but I want to draw everyone's attention to it. Let's see. And then Spencer will do his thing. You ready, Spencer? Yeah. And then I'm going to demo my bouncing ball app, because that's what you're supposed to be writing for Monday. And in particular, I want to talk to you about how to do bounces off of walls. And I'll show you how to do that in the bubble example that we're working on. And then I'll generalize it a little bit to all 4 walls. Any questions about anything before I get going? Let's see here. I think it was this one. Maybe not. I'm just guessing. So notice the change in color of the vertical lines as you go across, and the change in color of the horizontal lines as you go down. I mean, just very systematic. Just one of many things that you can do that we'll see here as we go through. Let's see. I think it was the static one. So Tong found an image on the web and then figured out how to bring it in to her sketch, and that's a really interesting thing to do. Chris did something sort of mathematical. So there's a little snowflake, which is pretty all by itself. But he put a different topology on the screen. He identified the top and the bottom boundaries of the screen, and so this guy will fall off the bottom and come back on the top. Go off the left, come back on the right. So he's identified the top and the bottom boundaries and the left and the right boundaries, and this is called a torus topology. Asteroids, I think, is played on a torus topology, the game Asteroids. Let's see here. All I have is all I have is names here. I don't really have reasons why until I see them. That was just kind of interesting, mesmerizing. I think your animation was also, I don't remember what it was. Oh, yeah. I do? Oh yeah, that resets it. I knew that. Thank you for reminding me, though. Let's keep going here. Took me a while to figure out how Eric was doing this, but I like it. I have not done this before. The fade is just repeated layers of 10% transparency, which is, I didn't know that that's how that worked, but that is how it works. So you keep putting on a layer of of 10% white transparency, and it causes the stuff to fade away. Very cool. Oh, and the static one, Eric's static one was also really cool. One of my favorites. Let's go here, and here, and here. Very nice. Okay, let's keep going here. Not sure what I liked about this one, but let's pull it up and see. Oh, that was just another really sort of complex static figure. I like the circles. Circles around circles kind of deal there. Pretty cool. And I believe his second sketch was also interesting, but again, I don't remember why. So yes, if you want to induce epileptic seizures, this might work. Anyway.
Can we make other people's sketches available so we can do them? Oh.
We will start doing that in the next assignment, because in the next assignment you have to put your sketch online. I could add something to the next assignment to make everybody put these online as well. I'll think about that. Okay, let's get rid of that. Let's see who else we're going to go after. Oh, speak of the devil, Lauren. This was one of, I think, the only one that used the Bezier, and the curvy lines or the wavy lines are created by Bezier curves, and it just adds a nice effect. Yeah, they are. Okay, let's. And in fact, I think I liked your animated one too. Yeah, if I do control, I think it'll put that kind of stuff. How careful were you with the colors on a particular square? Are they just random?
The colors are random, but I did overlap. I like made the
Okay.
So they overlap.
Got it. Anyway, that was cool. Jason. Jason was the animated one. Oh yeah. Hold the button down. The rocket goes up. Let the button off. The engines go off and it falls. That was cute. And you can even send it off the top and let it go and it'll come back. Okay. Carter. Just because I like bunnies. How did you know? And I think I also liked your dynamic one, so. There's some interesting effects in this dynamic one that I wanted to kind of point out to you. It's cool how it sort of slows down as it gets to the pointer and does a nice little park right next to the pointer. And then if I click, and you notice that the top cross is kind of, they wobble a little bit relative to each other, which is also a really interesting effect. So two really interesting things here, that relative wobbling and then the fact that this little guy, it's like a gnat, you know, just won't leave you alone. Okay. Let's keep going. Danielle. This one is good for just mesmerizing you. And it should be much larger. Okay, that's enough of that. Everybody wake up. I think I liked all three of these. I don't remember. Oh yeah, this one. Can I actually play this game or not? Okay. I'm actually like clicking, trying to like, damn it, I missed it again. Exactly. It's just terrible. Thanks, Danielle.
Yeah, someone told me it was a damage.
Yeah. And then the planet Uranus. Just pretty. Got the shading on the ball there. Yeah, not to scale exactly. So. Hold on for a second. So the fonts don't look the same as the ones on your computer?
Yeah, so I think they're just using the default.
Are you a Mac?
Yeah.
Yeah, so your system fonts are probably a little bit different. And it has a, I don't know, let me check your source code here a little bit and see how sophisticated you were with your font handling. Yeah, so you were using the cream, you know what it is? I don't have the font file. I didn't, yeah.
It's like on both of those.
Yeah. So it's just, you're right, it's using the default system font because you didn't send along the font file and I didn't bother to generate it. Okay. So font handling and processing is a little complicated if you want to use the non-default fonts. Okay, so getting out of there. Okay, one more. Had to go back to Kendall because she didn't send me her images. But I got them now.
Oh, you can move mouse and move monitor around.
Oh yeah, yes. And this background image you just got from somewhere, and the Mario you got somewhere, and the bubbles you put on there, and the Mario you put on the moving Mario thing. Yes. Okay. And then got to show the other one too. Not really sure, you know, like what's going on there, but go Stormtrooper. Okay. I can always rely on Kendall for mature and thoughtful. It is, absolutely. Thank you for that, everyone. Again, if I didn't throw yours up there, it doesn't mean I didn't like it. It's just didn't have time. Okay, any questions about any of those before I go on? Let's go back to the bubble example. So I think that's here and here and here and here and here. So this is where we left off last time with bubbles. All right, let's remind ourselves how this works. Initially, we started off with 100 bubbles, and then in the draw function, which again is running repeatedly, with 50% probability, I'm going to add a new bubble to the screen. And here we have a loop that goes through all of the bubbles in the array list and gets the bubble, draws the bubble, and updates its position. Does this over and over and over again. And then we talked about removing the bubbles from the top. And we didn't talk a whole lot about this. We just kind of took it for granted at the end there. We decided that it was a good idea to get rid of bubbles that went off the top, and then I threw this at you. But we didn't really talk about it. And I guess my question is, what's actually happening in this loop? You've got this remove thing, right? So think about, you've got this list of bubbles from 0 up to 100 or 1,000 or what have you. And you want to remove the 5th bubble. What's that process look like? Do I just pull it out and then there's an empty slot at the 5th slot? Or do I pull it out and does something else happen? Ideas? No ideas? Let's talk about it in the notes here. So let's say I have an array. And these are all bubbles. Here's the first bubble and the second bubble and the third bubble and so on. 1, 2, I forgot 3. It's like a Python movie. Okay. Now, suppose I've decided that this bubble right here needs to go. Does that just stay an empty slot in the array? What happens? What do you think happens? Just guess. Yeah, Chris.
We talked about doing this before manually, and the solution was to take 4 and write it down to 2 and delete 4.
Yeah, so one possibility is you take this guy and you put it here. Or the other possibility is that they both move up. And frankly, I don't really care which one's happening internally. The thing I want to point out is somehow that space is getting filled by stuff afterwards. Either they're all getting slid forward by 1, or you're taking the last one and dropping it into that slot. What I want you to do now is stare at this logic and think about potential problems with this logic. Yeah.
Well, if you had a whole array and you just wanted to remove the ones in the middle of it, then like in the middle of the screen maybe, then it might not be the ones on the edge, but just
That's okay, because we don't care about the order of these bubbles in particular. I'm not worried about how they're ordered, you know, first to last or whatever. But there is a problem with this.
If you remove 2 and then you put 4 into 2, you don't check 4.
Does everybody see that? What happens if I remove 2? Either I put 4 into 2 or I slide everybody up. But either way, I go back up here, and what happens to I? It turns into 3. And so whatever got put into that empty slot didn't get checked. Turns out to be not a super huge problem in this particular example, because it'll just go through the array the next time the draw function is called and probably check it then. So what the problem that this guy has is it will not catch 2 stale bubbles in a row. Doesn't catch 2 stale bubbles in a row. Is there an easy fix for this?
You need to put 4 for a while.
You could do that. There's an easier fix. But also inside the if statement. Sarah? Absolutely. Okay, think about what's going to happen. You're going to remove the ith bubble. Let's say it's the second bubble. So you remove the second bubble, and then the I turns into a 1, and then it goes back up to the top and turns into a 2 again. And it'll get that next stale bubble. Make sense? Okay. Let's see if that changes anything. I don't think it will. So the question is, we don't really know whether it was working or not. Is there a way that you can think of that we could figure out whether our stale bubble removal process is actually working as it should? Can you think of a way?
Could you just move rather than less than 0? Could you put it somewhere on the screen so you can see if they get erased when they cross that point?
Yeah, and in fact, that's the thing. That's what I'm building up to. What I'd like to show you is a debugging tool. We could simply print bubbles.size to the screen. And we don't have cout in processing. We have print and print line. Can you guess the difference between just print and print line?
One character versus whole string of characters.
That's a good guess. Not quite.
Well, print line will do it down to the bottom of the screen.
So we'll print. Print line will include an end line for you, and print won't. Just very small difference. Let's see what happens when we run it with this print line in place. Okay. See this? This is coming from the print line, and it's telling me the size of the bubbles array at any given time. Now, we know that we're continually adding bubbles to the list. So if we didn't have the removal thing in there, we would just continue. This number would continue to grow. But we see that with this continuous cleanup process, that we're kind of maintaining a steady number of bubbles. Why the variability? Where's the randomness coming from? From the randomness, right? It's coming from that random. We don't really know how many bubbles are going to be added at any given time. Let's see what happens if we get rid of our cleanup process. So now we're just back to drawing bubbles. We won't see any difference in the runtime. And that'll just grow in perpetuity. Way more bubbles than we need. It'd be interesting to see what would happen if we got rid of our little tweak. I suspect not much, but maybe I'm wrong. It might run a little bit higher as you get more and more consecutive bubbles, but you can imagine, right? What happens if you have a whole bubble array full of stale bubbles? It'll get every other bubble, and then on the next pass through, it'll get the rest of them. Maybe something like that. So, not having a huge effect, but you know, a subtle thing like that could cause you some issues, and it's good to know how these things work. Any questions about that? All right, Spencer, why don't you come on up and do your thing, and then we'll talk about bouncing bubbles next. Do you need your email or something? Okay, so let's go here. here, here, here. And let's log me out. It looks like I'm already logged out. Go ahead and it's going to ask you again. Just click, just click sign in or whatever. Yeah.
Why they go here?
Yeah. Maybe. Just guessing.
Seems reasonable.
Yeah, click on that. Good.
All right, so my presentation's on Linus Torvalds. So he got a computer science degree from University of Helsinki, and his interest in computers began when he got his own first computer. He kind of worked on tweaking its operating system to try to make it better than what he was, and he was actually kind of a hacker. I tried to find an example of this Cool Man game, but I couldn't find it. It's actually a clone of Pac-Man. And his thesis in college was titled Linux, a portable operating system, and he actually didn't want to name it that. But kind of like the group he was working with behind his back kind of decided that's what we're going to name it. And then finally he's like, all right. So this is the kernel. This is kind of like a simple version of it because in trying to read about it, it's kind of crazy terminology that was a little over my head. But basically, the kernel is between your devices and your applications, and it's just kind of a bridge that connects the two. And so for a Linux kernel, that's kind of what's underneath every device that runs on a Linux operating system. So we began the project in 1991, and as of, I believe last year, has over 15 million lines of code. It's mostly in C. Torvalds, he actually hasn't written that much of it. He's one of the top contributors to it, but it's only about 2% of the code, which isn't a lot, but at the same time, it's still like 300,000 lines or something like that. His main job now is just taking in what other people have to say and like what code they want to interpret, and then he just merges all these together and puts it in the final code. And it's an open source project, which I will get into later. And then the little penguin, that's kind of like the Linux logo. Its name's Tux. So a new version actually comes out very often. It's every 2-3 months, which is probably part of the what open source does. I mean, it's always being kind of tweaked and modified. And it's licensed under the general public license, which makes it so Torvalds can produce it and also like give it out to people that want to see it. So if you want to see the code of the Linux kernel, you're allowed to for free. And it's the operating system in over 91% of the top 500 supercomputers list. So it's a very powerful and efficient operating system. And if you were to recreate the Linux kernel, it's going to cost about $3 billion, just because with the open source, it's taken about like a little over 3,000 man years. So to recreate it in just like a normal setting, it's going to take forever. Then here is just a little diagram of all the kernels. So this is all the different versions of it. And as you can see, at first it didn't like get changed that much, but as time has moved on, they change it all the time. So there's been a ton of different versions of the kernel. So as I was saying about open source, Torvalds, as a copyright holder, he's allowed to study, change, and distribute the software, and he's able to do that for free, which is a pretty big deal because that's hard to do nowadays. It's you're not really gonna be able to see like Mac OS and be able to see the code. It's developed in a public, collaborative manner, and it's not only just individuals producing the code. There's also large companies that are kind of part of the team, I guess, of creating the code. It's in a lot of different places. It's in Android, that's derived from Linux. That's one of the more popular cell phone operating systems. It's at Google and Amazon. It's in the database for U.S. immigration offices. So really important, and also operating systems that are going to need to handle a lot of information and very rapidly. And he's pretty well known in the kind of computer technology realm of things. He got elected to the Internet Hall of Fame, which is pretty big deal. He got the Millennium Technology Prize, which they said is essentially the Nobel Prize in the world of technology. And Time Magazine recognized him as the 17th most important person of the century in their Time 100 and 2000. So he's a pretty big deal. That's it.
Questions?
So can you explain that graph first? Like, there's the bars.
This graph?
Yeah, that graph.
Yeah, so across the bottom is basically what version of the kernel is. So it started with 0.01 and now they're up past 3. And then each year, so in 92, like Cortex was 91, it came up 0.01. Then, you know, a little after 94, it came up 1.0. And it's just every
So
different.
Berkeley is an iteration on the kernel version.
Yeah.
Okay.
So it's like these are like, so the years obviously here, and then each like 2.034, 037, like those are the different versions.
I started down there at 1.0.
Oh.
I brought home my first Linux operating system on a stack of 100 3.5-inch floppy disks. Yeah. Those were the days.
Now it's all the way up here.
Yeah, other questions?
What does the kernel look like?
That I don't know.
It doesn't look like anything. It's you don't interact with it directly. You interact with it indirectly. So its job is to, when you ask for a file from the hard drive, it'll go to the hard drive and get the file. Or when you ask to load something into RAM, it'll go and load it into RAM. Or when you have 300 different applications running on your computer, it'll decide which application gets to use the processor at any given time. So it's very low level, and it's really high quality software, and it's free, and that's why it's on, you know, phones, right? Google or any Android phone, the phone maker doesn't have to pay anybody a license fee to use Linux. So, and when you're working on profit margins that are so slim, right? You can make a handset, a smartphone, and not have to pay $3 license fee to Microsoft. That makes a difference, believe it or not. So, other questions?
So do you think there's like do you think there are a lot of advantages of using Linux on phones then, like instead of iOS? Do you think that would be?
I think in the long term, I mean, you're seeing Apple's profits start to erode already, and I think it's largely because they can't hang with the free Android operating system. I think Android has some serious issues, some serious problems with it, but I think in the long run it'll dominate the handset market because it's free, and the economics will drive it that way. And I don't see Microsoft's made a few attempts to get into that operating system market, and then it just seems completely impenetrable to them. Apple kind of got there first and established this large market share, but Android is just over the months and years just eroding that market share. Apple's phones are too expensive, basically. Mm-hmm. And if they can get their costs down, then they might be able to compete. But right now, especially in developing countries, it's Android all the way, baby. Other questions? Okay. Thanks, Becky. Sort of an unassuming looking guy.
Yeah.
Okay. So let's revisit the current homework assignment, the one that's due Monday. And remember that when the user clicks on the canvas, you create a new ball with random x and y velocities. Gravity draws the ball down, and you're going to do some bouncing algorithms, and you're going to use a class to represent the balls. So you should be able to at least use the bubble example as a fairly close example. I should change this word to ArrayList instead of array. And some kind of above and beyond element. And most of you seem to have no trouble coming up with above and beyonds in this context, so that's been good. Let me show you my bouncing ball program, just to give you an idea of what it looks like. Let's go here, 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 and here. Okay, I'm not giving away too much when I show this, and I'm not going to show you the rest of my program, but here's what it looks like. Very plain vanilla. Oops, and I have to turn off my. I have some friction in there that I want to get rid of. All right, so we've got a ball that starts out, and if I click, I'll create a new ball, and you can kind of see that it had an initial velocity down and to the right. And if I click again, that one was more straight down. That one kind of went straight up, but gravity draws it down. It is random, yes.
Is there anybody that can interact?
Yes, there is, but I don't have that going right now. So interaction would be, what you mean by interaction is collision detection. So you want to detect collisions, and when you have a collision, you want the balls to leave the collision in a physically meaningful way. That would be a way above and beyond, but I'd be happy to see it. It's not hard. It's not hard. Okay? It's not hard. It's especially easy with balls, with round things, because essentially when two centers, right, when two centers get within 2r of each other, they're having a collision. So then what you do is you look at their locations, you look at their velocity vectors, and the collision calculation is quite straightforward. And then you just change their velocity vectors to reflect the outcome of the collision, and they move away. And in fact, that's kind of what's going on when you watch something hit a wall. When a center gets within r of a wall, I do a bounce. How do I do a bounce? Well, if it hits say the left wall, that's in the x direction, right? The velocity is in the x direction. So if it hits the left wall, all I do is flip the x velocity, change vx to minus vx. If it hits the right wall, vx to minus vx. If it hits the top wall, vy to minus vy. If it hits the bottom wall, vy to minus vy. Very straightforward, this bouncing thing. There's no friction here, and so these guys will just kind of sit there and bounce forever. And one of my above and beyonds was to add a cost to every bounce. So I'll put a fairly expensive energy loss into my bounces, and then make a bunch of them. And because there's this cost to bouncing, they will all just kind of settle down to the bottom and sit there. Their x velocities don't change, so they'll just kind of roll back and forth on the ground forever. I take it back. I think I have a cost for x bounces as well as y bounces, so they will not roll forever. But it'll take them a lot longer to die. So every x bounce is going to cost them a little bit as well. And the y bounces are done. Okay, let's talk a little bit about how to make this happen, and we'll go back to the bubble example. And we will get our bubbles to just, instead of going off the top, we'll get our bubbles to bounce off the top. And I'll show you what I mean by that. Let's go back to the example. All right, so everything's going to stay the same. In fact, I think what I might do is get rid of the initial 100 bubbles. Well, let me just comment it out. So if I comment it out, it looks a little bit more like this. You don't get this initial flood of bubbles. You're just getting sort of randomly generated bubbles. All right. So I talked about what happens with a bounce. I'm going to put my bounce stuff down here in the update position thing. And what I'm going to do is just check. So here's bounce code. And all I'm going to do is check a top bounce. So what do I mean by that? Well, if, let's see, if x gets within r of the boundary at the top, sorry, not x, but y. If y gets within r of the boundary at the top, there's going to be a bounce. What does that if statement look like? Y is within r of the top.
Height minus r.
Well, what's the top for the top is 0, right? So really, if y is just less than or equal to r, you're hitting the wall, right? Oops, r. You do, because you don't know how far it's going to jump in a particular update of, right? It might jump past that R boundary and into no man's land. So you just, yes. So if y is less than R, then I need a bounce. It's pretty straightforward. There are more sophisticated and more realistic ways of executing a bounce. The easiest thing to do is just make y equal to r. So if y tries to go past r, make it equal r, and then reverse the y velocity. So again, if the center of this guy gets within r of the boundary, then I'm going to move y to that boundary and reverse its velocity, and that'll cause it to very quickly, you won't really see it. If it goes into no man's land, it'll suddenly sort of jump to the boundary, and then it'll start going this way, and then it'll get drawn back up to the top. So what's going to happen here is I'm going to get a bunch of bubbles sort of collecting at the top, and none of them are going to get thrown away because they're never going to go past. So in fact, I can get rid of the old bubble code because no bubbles are going to go off the top with this bounce code. Let's see what this looks like. And notice that they keep growing. So it's going to get pretty messy in there. So let's knock back the growth thing a little bit. Oops. In fact, let's just get rid of growth altogether. Where did I do dr anyway? So let's make no growth. And the ones that start near the top never really get very fast, but the ones that start near the bottom and then get really fast and go all the way up, they're going to hit and they're going to come all the way back to where they started. It's not really particularly realistic, but
Or you could upside down stairs.
yeah. Okay, let's now I talked about the bounce cost. Let me show you how to do bounce cost. There's probably a better word for this, but if you can think of a better word.
Like elasticity? It's like how elastic it is.
Sure, let's call it elasticity. So we'll say it's 3/4 elastic, which means it's 1/4 losing energy. Okay, if you go down there, what we're saying is when we hit a wall, we lose some velocity. So it's not strictly negated, it's negated and shrunk a little bit. And let's see what effect that has. So it should start sort of accumulating at the bottom, I would imagine, or at the top, excuse me. And we are starting to see a whole collection of them. And if we had good collision detection, we could actually get accumulation. But we don't. They're all just going to sit down there and overlap with each other. So let's talk a little bit about what bounces would look like on the other four boundaries in the remaining minute here. So bouncing off of other boundaries. So we've seen already that in the top boundary would look like this. If y is less than or equal to r, then what we'll do is we'll just set y equal to r, and we'll reverse its velocity. What's the bottom boundary look like? What's the condition for the bottom boundary? And I'll remind you that there are two reserved words. There's width and there's height. And these reserved variables hold the width and the height of the canvas. Say again? Sure. So if y is greater than or equal to height minus r, okay, so if y is greater than or equal to height minus r, then you're in no man's land, right? The center of the circle itself must be hitting the wall if the center of the circle is above this value. So what should I set y to, again, in my simple model? Yeah, let's just set it equal to height minus r and velocity. Same thing, it's exactly the same. And you might think, well, how can it be the same, right, if I'm hitting the top versus the bottom? If this guy hits the top, what's the sign of Vy if it's hitting the top? It's negative, and so minus Vy makes it positive, which makes it go down. Right? Remember, down is the positive y direction. On the other hand, if you're hitting the bottom boundary, what's Vy? What's the sign of Vy? It's positive, so minus Vy is negative, which makes it go back up. And beautiful thing about physics and vector value quantities like velocity is we just need to address each component of velocity independently. So similarly, if x is less than or equal to r, then x is equal to r, and vx equals minus vx. And if x is greater than or equal to width minus r, then we will let x equal width minus r and vx equal minus vx. Grr. And these 4 checks together will get you bouncing off of 4 walls. Simple as that. All right, we'll talk more on Friday about getting your sketches on the web in particular.